Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll focus on GPU offloading through Cuda Fortran. Cuda, created by NVIDIA, is a parallel computing platform and API that allows for programming directly on GPUs. Cuda Fortran is an enhancement to the Fortran programming language, enabling it to utilize the features of Cuda directly. Previously, we mainly used directive-based GPU offloading with Open-ACC and Open-MP. However, our first exploration into GPU offloading involved language-based offloading, employing the Fortran do concurrent command. Unlike these approaches, Cuda is a kernel-based offloading that involves explicitly writing kernels to manage offloading. Before exploring Cuda Fortran, we must introduce a feature in Fortran known as subroutines. The Fortran program mxmsub uses subroutines. This program uses two specific subroutines, first initial to set up the matrices, and then mxm to perform the matrix multiplication. Subroutines are activated with the call command, followed by the subroutine's name, and the variables it uses, enclosed within parentheses. While it's commonly stated that variables are passed to the subroutine, no actual data transfer occurs. The variables remain in the main memory of the CPU cores, so both the subroutine and the main program share the same memory space. This detail is crucial to keep in mind when we explore the Cuda Fortran program later. In this example, the subroutines are included in the same program file, positioned after the main program's conclusion. The initial subroutine utilizes matrices A, B, C, and the integer variable n. Like the main program, the subroutine begins with a variable declaration and employs the implicit none command to ensure explicit type declarations. The variable n is defined as an integer with a kind value of 4, consistent with its definition in the main program. It is specified with an intent, indicating that n is intended as an input to the subroutine and will not be modified within it. The matrices A, B, C are declared as real numbers with a kind value of 8, matching their definition in the main program. They are dimensioned according to n and are intended to be outputs of the subroutine, meaning their values are established within the subroutine itself. In this example, the do loop utilizes the index variables I and j to assign values to matrices A and B. Additionally, the loop sets all elements of matrix C to 0. The subroutine concludes with the end subroutine statement, which returns control back to the main program. In the mxm subroutine, matrices A, B, and C, along with the integer variable n, are utilized. Similar to the main program, the subroutine starts with a declaration of variables and includes the implicit none command to enforce explicit type declarations. The variable n is defined as an integer with a kind value of 4, matching its definition in the main program. It is declared with an intent, signifying that n is intended solely as an input to the subroutine and will remain unmodified within it. Matrices A and B are defined as real numbers with a precision kind of 8, matching their definition in the main program. They are dimensioned according to n and act as inputs to the subroutine, so their values do not change. Matrix C, composed of real numbers of kind 8, acts as both input and output. Initially, all its elements are set to 0. After the subroutine executes, it contains the result of multiplying matrices A and B. Therefore, variables with intent in remain unchanged, while variables with intent in out are modified in the subroutine. The triple-nested loop for matrix multiplication updates the values in matrix C, making C the result of multiplying matrix A by matrix B. We have introduced the concept of subroutines in Fortran, and now we will examine a Cuda Fortran program for matrix multiplication, which utilizes Cuda for modules. We have chosen a matrix dimension of n set to 16,384. The program also uses certain block size parameters, which we will explain later. This program declares two sets of allocatable matrices. The first set consists of matrices used by the host or CPU cores, which are stored in host memory. The second set comprises matrices used by the device or GPU cores, and these matrices have a D in their variable names to indicate that they are located in device memory. We are using some Cuda-specific variables, which we will explain later. The matrices are allocated with a dimension of n. The initialization loop sets the values for these matrices. In Cuda Fortran, data transfer from the host to the device is straightforward and accomplished through simple assignment. The variable threads per block is set using a Cuda function called dim3, and we use block size variables to specify the number of threads in a block. Threads within a block share memory on the GPU. The variable numBlocks, which represents the number of blocks, is also set using the dim3 function and depends on the block size and the dimension n. By varying the block size in both the x and y directions, across the rows and columns of the matrices, we can assess the program's performance. This approach is similar to the loop-gang vector directive that we used in video number 10 during Open-ACC offloading on the A100 GPUs. The program now employs a subroutine to perform matrix multiplication on the device. This subroutine is activated using the call command followed by its name, matmul kernel in this case. In Cuda Fortran, triple angle brackets are used to launch a kernel on the GPU. Launching a kernel involves two types of variables. The first type, specified within the triple angle brackets, is the execution configuration, which sets the number of blocks and threads per block. The second type, enclosed within parentheses as in a standard Fortran program, includes the variables used for matrix multiplication. We use synchronization to ensure that all GPU cores have completed the matrix multiplication. After this, we can copy the result back to the host by setting the host matrix C equal to the device matrix D_C. Let's take a look at the matmul kernel subroutine, located in the program file after the main program mxm ends. In Cuda Fortran, the attribute's global qualifier is used to define a subroutine as a kernel that can be executed on the GPU. This attribute indicates that the subroutine can be called from the host and will execute on the device. When a subroutine is marked with attributes global, it can be launched using the triple angle bracket syntax, which specifies the execution configuration, such as the number of blocks and threads per block. The subroutine uses the variables a, b, c, and n, which are enclosed in parentheses. The first three variables are matrices, and the last variable n represents the dimension of the matrices. Note that the matrices passed to the subroutine are stored in device memory. Like the main program, the subroutine begins with a variable declaration and employs the implicit none command to ensure explicit type declarations. Notice that all variables in the subroutine are declared as residing in device memory. Although n is declared as a device variable within the subroutine, it is also defined in the main program. Therefore, we need to pass the value of n from the main program to the subroutine using the value attribute in the declaration. We also use the intent in attribute to indicate that this variable is an input and will not be modified within the subroutine. Matrices A and B are defined as real numbers with a precision kind of 8. They are dimensioned based on n and serve as inputs to the subroutine, meaning their values remain unchanged. These matrices are stored in device memory, so we don't need to use the value attribute because we are passing the matrices directly from the device. This approach is necessary because passing many real numbers as values using the value attribute would significantly affect the program's performance. Matrix C consists of real numbers with a precision kind of 8. It has dimensions of n by n and serves as both input and output for the subroutine, meaning its values are modified during the matrix multiplication process. Like matrices A and B, matrix C is also stored in device memory. The integer values of the index variables are determined by the execution configuration, which uses the number of blocks and threads per block. A single if statement replaces the two outermost loops in the matrix multiplication process, while the innermost k loop remains unchanged. This approach is similar to the loop collapsing technique we used in video number 18 during Open-MP offloading on A100 GPUs. In the GPU testing script, we specify the use of P100 GPUs on the Accel compute nodes. The offloading will utilize the Cuda Fortran method. The file ending is set to 1, and the matrix dimension is 16,384. The program will be executed once, with a billing factor of 6. The P100 optimization will be applied alongside the Cuda option. In the job script, we select the Accel compute nodes and request 1 GPU. We also request 8 GB of memory and choose to wait in the development queue. Recommended error handling is implemented, and the NV Fortran compiler is loaded. Lastly, the job script executes the testing script. We can now use the sbatch command to submit this job to the Slurm workload manager, and we see that the job has been assigned the number 13026557. Using the sq command, short for show queue, we can see that our job has computed for 15 seconds on the C78 node. After some time, we use the sq command again and observe that the job has completed. We can use the ll command to check if the job has produced the Slurm output file with the job number 13026557. We see that the Slurm output file has been generated, and we can view it using the Emacs editor. The Slurm output file contains some warnings and notes which we can remove to enhance clarity. The testing Python script outputs the compilation command. The wall time for this Fortran program is approximately 48 seconds. We can present the wall time of this test in a table with block sizes of 16 for both X and Y. By varying the block size, we can observe the wall time for different configurations. As shown, the wall times can differ significantly. In this test, we employed kernel-based offloading, which requires explicitly writing kernels to handle offloading. While other methods, such as language-based and directive-based offloading, may offer better performance, kernel-based offloading can be advantageous for more complex computations or kernels. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos. We can copy any of these files, but let's try copying the Fortran program mxm to the home folder. Then use the cd command to return to the home folder. Verify the copy with the ll command to confirm that the program is now in the home folder. In the next video, we will provide a summary of the various GPU offloading methods we have used. I am looking forward to the next video, wishing you all happy computing in the meantime.